Water by itself is a poor cleansing agent. In plain water, ring around the collar, a fat is plain stubborn. It just won't dissolve. Why is that? Let's start by looking at what we mean by dissolve. One compound can be dissolved in another if the molecules of the two compounds can be mixed randomly and evenly. The compound water is a small polar molecule. Polar because the electronegative oxygen has a stronger affinity for electrons than the two hydrogens. The result is that the slightly negative oxygen of one water molecule is attracted to the slightly positive hydrogen of another, forming a hydrogen bond. Hydrogen bonding builds up a network of electrostatic attractions. However, when non-polar molecules, such as the hydrocarbon chains found in fats and oils, encounter water, they cannot worm their way into the hallowed space between the water molecules, which is a long coming about to saying water and oil don't mix. Now let's take a closer look at the grime on that collar. An oil or fat is composed of three long-chain carboxylic acids called fatty acids, tied to glycerol by means of ester linkages. In most fat molecules, the long hydrocarbon chains have no double bonds and are said to be saturated with hydrogen. Oil molecules have varying numbers of double bonds, and with fewer hydrogens are said to be unsaturated. Both fat and oil molecules are nonpolar, and as such cannot participate in hydrogen bonding with water. If, however, we could send the end of the molecule, it could cut a swath through the hydrogen bonds in water. The solution, ironically, calls for fighting fat with fat, an idea as old as the ancient Egyptians, who mixed animal fat with potash to make soap. We'll now examine this ancient recipe from the perspective of modern chemistry. Start with the prime ingredient, an oil or fat molecule, and introduce a fat buster, a base. If sodium hydroxide is dissolved in water, the sodium cation and the hydroxyl anion will dissociate. Three negatively charged hydroxide ions are now free to cleave the fat molecule by breaking the ester linkages. Once broken, the sodium cation is attracted to the negative charge, forming a soap molecule. Two more reactions, and two more soap molecules. Now, the soap molecule has an ionic head and a non-polar tail. While the hydrocarbon tail remains oil-soluble, the ionized head is water-soluble. This is a grease slick attached to a collar immersed in water. Release the soap molecules, and they align themselves so that the non-polar ends tail in to form a sphere called a micelle. Through the agitation of washing, the micelle envelops the oil glob, with the molecules realigning themselves so that the non-polar ends penetrate the grease. The envelopment continues, and a much larger micelle is formed. Since the surfaces of the micelles are negatively charged, they are attracted to the polar water molecules. And the micelles repel each other as well, because they contain similarly charged peripheries. Note then that oil isn't really dissolved in water. Rather, it is converted into discrete, suspended gloves, transported by water and swept away.